Good afternoon. Today we are going to continue the discussion of hypothesis testing for proportion, and then we're also going to finish the hypothesis testing for mean. So let's first review what we talked about last time. Last time we talked about applying the critical value method to test the claim about population proportion. The example we did was test the claim that there are more red team members. According to our class results, out of 9 students who participated, 6 of them obtained a red card. And then based on our sample results, we want to see whether or not that there are more red team members in the true population. So first step is set up your hypotheses. The null hypothesis, which is denoted by H0, is p equals 0.5. This is because the statement is about proportion, so we use p. It's a null hypothesis, H0, so it's always going to be an equal sign. And then the 0.5 comes from the assumption that this is a fair standard deck of cards, meaning you have equal number of red cards and black cards. As a result, the probability of getting red cards should be 50%, which is 0.5. That's the default value. The alternative hypothesis H sub 0 is determined by the claim that we're trying to test. We're trying to test that there are more red team members, meaning that the proportion of red cards should be higher than 50%. So we have p greater than 0.5. Once you have your hypothesis set it up, then you know this is, let's write it over here. This is an upper tail test because it's greater than. It's an upper tail test. The significance level alpha is given by 0.05. So we follow the formula, write down the values that we're going to use for our formula, and it's the sample size. We only have 9 students participated. P hat is the sample proportion of red cards. So we have 6 students out of 9 obtained a red card. Therefore, the sample proportion is 6 over 9, which converts to about 0.667. Next one is P. This one is the P without hat. It represents the population proportion, which is the default value in our null hypothesis, and it is 0.5. As for Q, it's the complement of P, so you simply do 1 minus P, and then you also get 0.5. Once we have all these 4 values, we plug into the formula to calculate the test statistic z-test. P hat minus P divided by radical PQ over N. Make sure you follow the order. P hat is 0.667, P is 0.5, so you subtract them, divided by square root of 0.5 times 0.5 divided by 9. So if you use your calculator, you will get approximately 1.00 for your test statistic. Next step will be defining the rejection region. That means you first have to do a graph. Since we already determined that this is an upper tail test, your graph will look like item C right here. So your graph will look like C. The shaded region is the right tail. Next thing to do is find out the critical value. I gave you this table right here. This table tells you the critical value that you're going to be using for this course. First, significance level alpha, it's given by 0.05. Second, the type of hypothesis testing that we're conducting is an upper tail or right tail test. Therefore, it's one-tailed. The critical value is the intersecting number, which is 1.645. So that is our critical value. Once you have the critical value 1.645, you mark it in the graph above. So I marked right here 1.645. This is my critical value, and I shade everything to the right because it's a right tail test. And then we highlight the test statistic, which is 1.00. Since 1.00 is less than 1.645, your green little bar is going to be to the left of 1.645. And you can mark that as your z-test. And then once we have this graph, we're going to make a decision. Since our test statistic, which is the green part, is outside the rejection region, the blue region, we fail to reject null hypothesis and conclude that there is not sufficient evidence to support the claim that there are more red team members. In other words, our sample results, it's not very surprising. It's not convincing enough, or at least in statistics, that deck of cards that we have used in our last session is unfair. So that's basically what we did last time. We applied the critical value method. Hopefully you did your homework without any problems. Today we're going to use two more methods to conduct the same hypothesis testing. We will start with something that we're familiar with, which is the confidence interval method. The claim is still the same thing. We test the claim that there are more red team members. We use significance level alpha 0.05. The hypothesis, it's the same as what we used before. So the null hypothesis p equals 0.5, alternative p greater than 0.5. And again, this is a one-tail test, or you could say right tail, it's up to you. Sample proportion, we already computed earlier, 6/9, which is approximately 0.667. Q hat is 3/9, which is about 0.333. And then we are constructing which confidence interval. So you have to actually look at the confidence level. How do you determine the confidence level? We have a table that I provided for you. Our significance level is 0.05, so it's right here. And then our hypothesis test is a right tail test or a one tail test, which is right here. Therefore, you take the intersecting number, 90%, and that is your confidence level. So what we're going to do is we're going to put 90% right here. If you ever wonder why, you could do a visual. So conduct a normal curve like this, and then mark center as 0. Mark the type of hypothesis testing that you're doing. We're doing upper tail, so you're going to do a vertical line segment right here. This is your Z crit, and we are shading everything to the right. Shading everything to the right. Because our significance level is 0.05, so this area is 0.05. By the symmetry, the left hand side, this tail also needs to be 0.05, given that I have negative Z crit right here. So the critical value, you have plus and minus in this graph because you have 0 in the center. And then you could actually calculate the area in the middle. The two areas on the two ends, if you add them up, it's going to give you 0.1. So that basically means the area in the middle is 0.9. What is 0.9 percentage? It's 90%. So that's how you know that you're constructing a 90% confidence interval. Now let's fill in the sample statistics. First one is N. N is the sample size, so we have 9 students participated. Critical value is the same as before. If you remember, it's from this table. So our significance level is 0.05. It's a right tail test. So critical value 1.645. Let's put over here 1.645. And then we plug it into this formula to compute the margin of error. Critical value 1.645 multiplied by square root of p hat, which is 0.667, times q hat, which is 0.333, divided by n, which is 9. And then you're going to round this to usually 4 decimal places, so you could pause this video and calculate, and then compare your number with mine. I'm going to calculate on my calculator. 1.645 times radical 0.667 times 0.333 divided by 9, and you hit enter. So according to my calculation, my margin of error is approximately 0.2584. If you got this, or if you got something very close to this, that means you're correct. So this is our margin of error. To construct the confidence interval, margin of error is the most important part, as you may remember. To find out the lower bound, you start with your sample proportion, which is 0.667, and you subtract our margin of error, which is 0.2584, and you obtain your lower bound. So let's find out what lower bound is. 0.2584. According to my calculator, I got 0.4086 as my lower bound. Upper bound, instead of subtracting, you're gonna add. According to my calculator, it's 0.9254. It's a pretty wide confidence interval, I would say, because our margin of error is about 26%. And that's because our sample size is really small. So we have a very large variation in our confidence interval. Let's put those two numbers together. Lower bound 0.4086, upper bound 0.9254. What that means is that according to our estimate, the true proportion of red cards in that standard deck of cards, or quotation mark standard deck of cards, is between about 41% and 93%. That's a pretty huge interval. Does the interval contain the claimed value in H0? Which is very important because that's going to help us make a decision. If you look at the claimed value in the null hypothesis, we say that by default it's going to be 0.5. That's the proportion of red cards if it's a fair standard deck of cards. Our interval, yes, it does include 0.5, right? If 0.5 is in the interval, it basically means 0.5 could be the true population proportion of red cards. What that means is you cannot say that the null hypothesis is not correct because the value in your null hypothesis is part of your estimate. Therefore, our rejection decision will be fail to reject the null hypothesis, just like our conclusion that we had last time, fail to reject. And then underneath the number 5, we have this box, which I summarized the confidence interval method. We reject the null hypothesis when the confidence interval does not include the claimed value. So if 0.5, let's say, is not in the confidence interval that we constructed, then we could say that our null hypothesis, that 0.5, is not correct because it's not part of your estimate, and of course with a certain confidence level. We fail to reject null hypothesis when the confidence interval includes the claimed value in H0, which is the case that we have above. The confidence interval does include the claimed value 0.5, so we cannot reject the null hypothesis. And we basically got the same conclusion that there is not sufficient evidence to support the claim that there are more red team members. And that is the confidence interval method. Confidence interval method usually gives us an informal way to make rejection decisions based on your sample data. The last method we're going to talk about is the p-value method. This is the most popular method. If you're ever going to read a scholarly article on statistical studies, chances are you're going to see something called the p-value. They're going to report the p-value along with the confidence interval. P-value, as we said before, it's the probability of observing something as extreme or more than what you observed based on your sample, assuming that the null hypothesis is correct, which is based on the rare event rule. If our p-value is extremely small, less than the significance level alpha, then we will reject the null hypothesis. Otherwise, we fail to reject. So let's look at the p-value method right here. What is the significance level alpha? So we have been using 0.05 for this exercise. P-value, what is the p-value? So for p-value, you could use the z-table to find it out. our test statistic, if you remember from this part right here, is 1.00, right? And it's a right tail test. So you're basically finding out the p-value, basically finding out what is the probability of z greater than your z-test, which is 1.00. And you're going to read z-table to find it out. So let's go to z-table. Z-table first, let me get rid of these things that we used for other problems. The z-score is 1.0, so it's right here. And also the last digit is also 0. Therefore, this is the reading from the left, 0.8413. 0.8413. So let's go back to our handout. You could mark a graph right here. This is 1.00. We shaded everything to the right. And we find out that the left-hand side is 0.8413. To find out the yellow region, which is the p-value, this is the p-value, because it's a right tail test, is 1 minus 0.8413, and that's 0.1587. Alright, so let me actually double check if it's correct. 8413, yes. So it'll be 1587, right? So it's alright. This is our p-value, 0.1587. If you use technology, you will get something more accurate, which is 0.1582. Which is not a big difference, as you can see. Is p-value smaller than alpha? No, right? Because 0.1582 is definitely greater than 0.05. Therefore, we fail to reject our null hypothesis. The summary of a p-value method: we reject null hypothesis when p-value is less than alpha. We fail to reject null hypothesis when p-value is greater than alpha. And that pretty much summarizes the handout from last time. We introduced two more methods, the confidence interval method and the p-value method. There is a little catch here. If you apply confidence interval for proportion, sometimes you will get opposite conclusions by performing other methods like the p-value or the critical value method. This is because the formula that we use when constructing confidence interval is slightly different from the one that we have for hypothesis testing, which is basically coming from the denominator right here. If you look at it, this is PQ divided by N. We use population proportions. But when we construct confidence interval, we use p hat divided by p hat q hat divided by n. So we use sample proportion instead. That's why sometimes you might get different conclusions. I just want you to be aware of that. Alright, finally, we're going to move on to today's topic. Today's handout is 7.2, hypothesis testing for mean. So we did proportion, now we're going to do mean. For mean, if you remember the confidence interval, we apply t-distribution instead of z. So it's the same thing over here. When we conduct hypothesis testing for mean, we will use t-distribution as well. Let's look at a class example that we actually collected at the beginning of the semester. Recall that we did a survey on the commute time to BMCC in minutes. If you remember at the beginning, there is one question, survey question, asking you how long does it take for you to commute to BMCC on average. We're going to apply both confidence interval method and p-value method to test the following claim. The significance level is 0.05. The claim says that the mean commute time to BMCC for all for all students is greater than 45 minutes. So basically saying that it's going to take everyone more than 45 minutes to reach BMCC on average. That is our claim. I already computed sample statistic for you. Mean, which is the sample mean, is 52.6667. I would say our class sample mean is pretty high. As you can see, it's definitely way higher than 45 minutes. So there's a chance that we might be able to reject our null hypothesis, but you never know. Standard deviation, which is the sample standard deviation S, is 29.8727. Our standard deviation is pretty big, meaning that when we construct our confidence interval, our margin of error will also naturally be pretty big, which makes it harder for us to reject the null hypothesis. Last one, the sample size n is 15. Let's follow the procedure. First, null hypothesis. Since we're talking about mean, we're going to use mu for our parameter. In the null hypothesis, it's always going to be an equal sign. And the value is given by the claim, which is 45 minutes. So our null hypothesis, mu equals 45. Moving on to alternative, the value in alternative must be 45. We just need to figure out the inequality. The question says greater than 45 minutes, and that's exactly our inequality symbol, greater than. So we completed our first step, setting up the hypotheses. Step number 2, write down these descriptive statistics, which are conveniently listed on the right hand side. N is 15, X bar is 52.6667, sample standard deviation 29.8727. We're going to construct, so here you have to figure out the confidence level. You could use the table that I gave you, or you could do a little sketch like this. Our significance level is 0.05 and our alternative hypothesis is greater than. So we have a right tail test. And if you shade everything to the right of this line segment, the value right here is 0.05. By symmetry, the value to the left also going to be 0.05. If you add them up, it's going to be 0.1 on both ends. Since everything underneath the curve adds up to 1, that means in the middle it has to be 0.9, which is 90%. So we have it, 90% confidence interval. Let's write 90%. But again, you could use the table that I gave you last time. You could use that as well. Next, we're going to determine sample statistics that are necessary to find out the margin of error for confidence interval for means. First, degree of freedom. Degree of freedom, if you remember, it's simply n minus 1. In this case, will be 15 minus 1, that's 14. Alpha 0.05. We're going to use these two pieces of information to find out the critical value. So remember, 14 alpha 0.05, and it's a one-tail test. So you're going to look at area in one tail is 0.05. Let's go to our t-table. Degree of freedom, let me get rid of these marks. Degree of freedom is 14, so it's this row right here. And then we're going to look at area in one tail, because we're doing a right tail test, not a two tail test, is 0.05, which is right here. And then you're going to check out the intersection of these two, which is right here, 1.761. So that is our critical value, 1.761. Let's go back to our handout. .761. Moving on to the margin of error, we're going to plug in critical value 1.761 multiplied by sample standard deviation, which is 29.8727, divided by square root of 15. Let's calculate what this is. Alright, so according to my calculation, I got 13.5828. If I keep 4 decimal places, you might get something slightly different. As long as it's close, that's good enough. And then we're going to calculate the lower bound and upper bound. Lower bound is the point estimate, which is sample mean, 52.6667. Subtract your margin of error, 13.5828. Let's calculate that. Alright, we got 39.0839. So that is our lower bound. Upper bound, instead of subtracting, we are adding. And that will give us, so let me write this first. That will give us 66.2495. Therefore, our confidence interval is 39.0839 to 66.2495. As we expected, it's a pretty wide confidence interval. Does the confidence interval contain the claimed value in null hypothesis? Our claimed value in null hypothesis is 45. Unfortunately, it does. So if you remember what we discussed earlier, the confidence interval method, if the confidence interval contains the claimed value in null hypothesis, we fail to reject the null hypothesis, H0, and conclude that there is not sufficient evidence to show that the mean commute time to BMCC for all students is greater than 45 minutes. So that's basically the rejection decision. The p-value method is relatively easier as long as you have access to either technology or z-table. So I'm going to give you the p-value for this one right away. The p-value for this one, if you calculate, it's approximately 0.1686. And again, I use technology to calculate, so it's pretty easy to display. The significance level alpha 0.05. Actually, I wrote it in the wrong place, right? P-value 0.1686, and apparently p-value is not smaller than alpha because 0.1686 is not less than 0.05. Therefore, same conclusion, we fail to reject H0. If your p-value is less than alpha, then your decision will be reject null hypothesis. Comments are confidence interval method and p-value method. Confidence interval method is convenient when you want to perform a two-tail hypothesis test. But if it's a one-tail test, you have to adjust the confidence level by either doing a sketch or look at the table that I gave you on the previous handout. P-value method is convenient when you have access to technology, which most of you guys should be able to conduct. For hand-performed hypothesis test, we highly recommend that you apply the critical value method, which is the next part that we're going to cover. Critical value method, we're going to apply critical value method to test the same claim that the mean commute time to BMCC for all students is greater than 45 minutes. Let's set up the hypotheses. Since this is about the mean, so our parameter will be mu in our hypotheses. Null hypothesis is always going to be an equal sign, and the number is 45. The alternative, it's already saying greater than 45. As you can see, these two hypotheses is the same as what we have over here for the confidence interval method. Next, significance level alpha, which is 0.05 given by the problem. And then next, we're going to write down these values to prepare us for the computation of test statistic. Sample size n. Sample size n, in this case, we have 15 students, so n is 15. Sample standard deviation for the commute time. Let's actually, let me actually look at what it was. So it's right here, commute time. Standard deviation 29.8727. And then we have sample mean 52.6667. And then finally we have that mu, which is given by the value in your null hypothesis, and that's 45. Oh no, my OneNote crashed again. Alright, so I have to reopen OneNote. Just give me a second. Alright, so we're back. The value for mu will be the default value, which is 45. So you just put 45 there. And now we are ready to calculate the test statistic. So let's plug it in. X bar is, oh, this one, they got rid of my decimal place. So let me rewrite that. It's 0.6667. So that is our sample mean X bar, 52.6667, minus the mu, which is 45, divided by standard deviation, that's 29.8727, divided by square root of n, which is 15. Let's compute this on my calculator. So you're also going to compute. Let's see if we will get the same answer. Alright, so for this particular one, let me just double check my computation again. Divided by square root of 15. Okay, so I got, if I keep 4 decimal places, is 0.9940. 0.9940. That's my margin of error. Since it is, so you just look at the alternative hypothesis, what the sum is, it's greater than. Since it's a one-tail test, or you could say right-tail test, but the more important part is one or two-tail. It's one tail. We should look into area in one tail from t-table. The degree of freedom is n-1, that is 14, and the area in one tail is alpha, which is 0.05. So the critical value is, we actually did that earlier. Let's just go back to the table to double check. Degree of freedom is 14, area in one tail 0.05, critical value 1.761. All right, and then we're gonna graph our rejection region at this point. So you could do a t-distribution, which is just like a normal distribution. In the middle, of course, you have 0. Let's mark our critical value. Critical value 1.761. So I'm going to mark it right here, 1.761, and then do a little bit of vertical bar. Highlight everything to the right because it is a right tail test. And this is our critical value, z-crit. Then let's mark our test statistic. Test statistic is 0.9940. So apparently it's to the left of 1.761. 0.9940. This is our z-test. Apparently, the test statistic does not fall in the rejection region. So you could say since t-test falls actually is not in the rejection region, we fail to reject H0. It's the same conclusion as our confidence interval method and p-value method, as you may remember. And conclude that, so here's something interesting, right? When you conclude, since we fail to reject the null hypothesis, meaning that we cannot show that mu is actually greater than 45. So what you could say is, you could say there is not sufficient evidence to support the claim that, and then you just copy the claim, the mean commute time to BMCC, the mean commute time to BMCC for all students is greater than 45 minutes. So that's pretty much our conclusion. There is not sufficient evidence to support the claim that the mean commute time to BMCC for all students is greater than 45 minutes. And it's the same conclusion as if we use confidence interval or p-value method. They're all giving us the same decision, fail to reject the null hypothesis. Some of you might have concerns about the conclusion. Everything else is pretty straightforward if you follow the steps, but the conclusion sometimes could be a little bit tricky, right? What kind of conclusion should I write? That could be a common question. So don't worry, because I have a table on page 4 that's going to help you write your final conclusion. Wording of the final conclusion. So you just have to match the condition with the conclusion template. We could use our example as a demonstration. Our example is testing the commute time, whether or not it's greater than 45. That claim is H1. So if you remember, that claim is H1. It's the alternative hypothesis. And we fail to reject H0. So the condition that we satisfy is the second condition in the table. The original claim saying that commute time is greater than 45 is our alternative hypothesis H1, and we fail to reject the null hypothesis H0. Therefore, when you write your conclusion, you're going to use this template right here. There is not sufficient evidence to support the claim that, and then you just copy the original claim, which is the mean commute time to BMCC for all students is greater than 45 minutes. And that's pretty much how I got my conclusion right here. So if you just match this with the table, you will see it's exactly the same template. Alright, so that pretty much concludes the hypothesis testing for mean. For your homework, it's this page right here. The class survey suggests that the average age of all 15 students in this Math 150 section is 21 years old. Yes, it's exactly 21 years old for the average. With a sample standard deviation of 5.3586. Apply the critical value method to test the claim that the mean age of all BMCC students who are taking, alright, so this is a typo, who are taking Math 150 this semester is less than 20 years old, using alpha 0.05, and it's due next class, which is Friday. Make sure you submit before Friday. And this is another hypothesis testing for the mean. I already gave you all the sample statistics. You basically just plug it in. The only thing you need to worry about is the critical value. But the critical value, since we use the same significance level and it's the same number of sample size, your critical value is probably the same number that we used in class. So I'm just secretly telling you that. Make sure you verify if that is correct. And then you're going to make a decision by graphing the critical region or the rejection region. See if your test statistic falls in the rejection region. And then you use the template from the top from this table to write down your conclusion. So some concluding thoughts on critical value method. We reject null hypothesis when test statistic falls in the rejection region. We fail to reject null hypothesis when test statistic does not fall in the rejection region, or you could simply say falls outside the rejection region. So that's why I highly recommend that you always visualize your rejection region and your test statistic so that it's very easy to see whether or not you should reject or fail to reject the null hypothesis. On page 4, in addition to the table for your conclusion, I also have an optional homework assignment that you can practice with. This is only if you're interested in getting more exercises. You're going to use the sample data that we got at the beginning of the semester. So check out the class notebook. It's in the first lecture, and there's an Excel file that you can download. Once you download, then you're going to compute some of the sample statistic depending on the claim. So claim 1 is the mean number of siblings. This is the population parameter that we're trying to estimate, mean number of siblings. So you're going to actually calculate that. The second claim is the same, very similar to what we just did in class. It's about the mean age of all BMCC students. Instead of saying less than 20, the claim right here we have is greater than 20. So would that change our decision? Give it a try. And that pretty much concludes Chapter 9, Hypothesis Testing for Proportion and Mean. Make sure you finish homework and then submit before this Friday. I will see you on Friday, hopefully in person, so that we don't need to watch this asynchronized video. Alright, thanks for watching.